Hello everyone, this is Deekshita. Today I am going to present my embedded system internship project titled AC controller using PIC 16 F877A. This project demonstrates how a microcontroller based system can be used to control appliances similar to real air conditioner. In this project, we have controlled phone made peripherals, a cooler, heater, buzzer, and an LCD display using the PIC16 F877A microcontroller. Instead of using physical hardware, the entire project is designed and tested using PICSIMLab, which is a simulation tool. This helps in understanding the working of embedded systems without the risk of damaging components or increasing cost. Through this project, I focused on understanding real-world embedded control concepts such as peripheral interfacing, control logic, timing, and system initialization. Although it is a simulation-based project, the behavior closely resembles that of an actual embedded AC control system used in real applications. The main goal of our internship were not just to complete a project but gain strong fundamentals in embedded systems. The first goal was to understand embedded system architecture, meaning how hardware like microcontrollers interact with software to perform a specific task. The second goal was to learn microcontroller programming using embedded C. This includes understanding registers, I/O ports, delays, and writing structured embedded programs. Another important objective was interfacing and controlling peripherals such as LCDs, buzzers, and output devices. This project helped me understand how a single microcontroller can control multiple devices at the same time. Finally, I aim to use industry standard tools like MPLabX IDE, XC8 compiler, and PiximLab for simulation and debugging. These tools are commonly used in embedded product development, so this internship helped me bridge the gap between theory and practical implementation. Before going to the project details, it is important to understand what an embedded system is. An embedded system is an dedicated computer system designed to perform a specific task. Unlike general purpose computers, it works within real time constraints, meaning it must respond with a defined time. Embedded systems are everywhere in our daily life. Examples include air conditioners, washing machines, microwave ovens, automobile medical devices, and IoT systems. An embedded system mainly consists of two parts: hardware such as microcontrollers, sensors, and actuators; firmware, which is the embedded software written in languages like embedded C. This AC control project is a simple but effective example of an embedded system where the microcontroller continuously monitors and controls outputs based on programmed logic.
Hello everyone, I am Nayani. This is about the project requirement where PIC16F8778 microcontroller is a core controller which includes 16 into 2 LCD to display the system's status and coolers, heater, buzzer used as an output. PiximLab with MC Lab 2 board, we use it for stimulation, and last one is for coding. This is a system design where PIC16F877A acts as a main control unit where LCD display temperature and system messages, cooler turn on for high temperature, heater turn on for low temperature. Buzzer gives alert indications. Board information about MC Lab 2, where virtual PIC development board in Pixim Lab. There's no physical hardware required, supports PIC's microcontroller stimulation, and it includes LCD, LED buttons, and also buzzer, useful for embedded system learning and testing. This is about the development process. It starts by writing embedded C code in MPLab IDE and compiling it using XC8 compiler. After successful compilation, a HEX file is generated. This generated file is loaded into PiximLab using the MCLab2 board, and the stimulation is run to observe the output on LCD, LED, or buzzer.
Hello everyone, this is Ravya. Let me explain the tools and technologies used in this project. I developed the entire applications using MPLab X IDE. which is used for writing, building, and debugging the embedded C program. This IDE makes it easy to manage the project, check errors, and test different logic conditions. And next, the XE8 compiler is used to convert the embedded C code into the mission level instructions that are compatible with the PIC16F877A microcontroller. Without this step, the microcontroller would not be able to understand the program. For testing and validation, I used PixSimLab, which provides a realistic virtual hardware environment. For example, I could test the LCD display, fan operations, and buzzer alerts without connecting real hardware. This entire control logic is implemented using embedded C, which allows efficient and reliable control of all the connection devices in real time. Coming to the implementation of the system. When the system is powered on, the microcontroller first initialize the LCD and display the system status. This helps the user immediately understand the system is active and working. In this initial stage, the cooler is enabled and the heater remains off. Based on the default control logic, the install conditions ensure safe and predictable system behavior, and the buzzer is indicated to different system states and mode changes. For example, whenever the system changes switches between operating modes, and the buzzer provides a short alert to notify the user, and the switches of all devices is controlled using delay based timing logic, which is written and executed using embedded C. This timing control ensures smooth and stable operation of the system. In this slide, I will explain the complete working of the AC controller. Once power is applied, the system becomes active and continuously executes and the program control sequence. The current operation status is displayed on the LCD, which improves user interaction and clarity. This allows the user to know exactly which device is active at any moment. The cooler turns on and the fan begins to rotate, simulating the operation of a real air conditioned system. And whenever there is a change in the operation mode, the buzzer provides an alert at an indication. After a predefined delay, the cooler turns off and the entire control circle repeats automatically. All these operations are handled efficiently by the PIC microcontroller using embedded C program without a manual innovation. Now, let me discuss the advantages of using simulation in this project. First one is one of the main advantage is that there is a no hardware cost in this project, which makes the project economical and accessible for learning. And next one, simulations also provide a safe and risk-free environment for testing embedded applications. For example, even if there is a logical error in the program, there is a no risk for damaging components. And third one is debugging and fault identifications are much easier compared to the physical hardware. This helps is faster development and better understanding of the system. And fourth one is design modifications can be implemented quickly, which significantly speeds up the overall development process. Hello everyone, this is Vashita Reddy.
The demonstration starts by opening PIC SimLab with the PIC 16F877A MCLab2 board. This board is chosen because it already integrates all the peripherals required for an AC controller demonstration, such as an LCD, push buttons, a buzzer, heater indicator, and a cooler fan. Using this board allows us to simulate real hardware behavior without external connections. So to choose the board, we will choose the board in our MPLab IPE, where we have to select the device we need and all the tools required. So after selecting the board, the hex file is generated from the MPLab X is loaded. So in the MPLab X IDE, we write the required code and we generate the hex files. This step is necessary because microcontrollers do not understand C code directly. So they execute the machine level instructions. Once the hex file is loaded, so once we select the and load the hex file that we have created through the codes, and we have to load it. So I've already loaded it. So once the hex file is loaded, the reset button is pressed. Reset Reset is intentionally used instead of restarting the simulator because it closely mimics how a real-world embedded system behaves when power is applied. Pressing the reset ensures the microcontroller starts executing the program from addressing 0 and all registers return to their default state. After reset, the LCD turns on, initially appears black. This confirms two important things. First, microcontroller is running correctly, and second, the LCD hardware is properly powered. So in the absence of the text initially is expected because the program controls when and what data should be displayed. So at present we are testing all the LEDs, and now the buzzer is also activated. So now we have to test the buttons. So after this, now we have to check if we have to now do this. We have to click on RBO button. Now we have testing EEPROM kit, and we have to select S2, test the serial, S2 again. So now it is testing. After fixed delay, the cooler buzzer turns off. So the LCD updates to show, which is done to provide user feedback. In real world embedded systems, visual confirmation is essential so the user understands the current operation mode without guessing. So this at present shows the current temperature. So now the heater is high. So as we can see, the temperature keeps on increasing. And when the cooler turns on, then the temperature is increased. So we can see the cooler turning on. So the temperature decreases. As it leads to the threshold temperature, the cooler slowly turns off. So this delay-based switching, as we can see, the cooler is turned off. So the LCD then confirms the system that entered an ideal or a standby condition. This on and off cycle repeats continuously, which demonstrates how embedded systems typically run in loops, continuously monitoring and controlling hardware rather than executing ones like a desktop programs. So as per the code, we have done the coding part in the MPLAB X IDE. So this program begins by including the xc.h because it provides access to all the hardware registered of the PIC16F877A. Without the file, the compiler would not recognize registers like port C and TRISC. The external F frequency is set to 2 megahertz because delay functions such as delay ms rely on this value to calculate accurate timing. If this value does not match the simulator clock, delays will incorrect, which could make the system appear non-functional. The LCD header file is included. The LCD header file is included separately to keep the LCD logic modular. This separation improves readability and allows the LCD driver to be reused in other projects without rewriting code. So the port C is configured as an output because it controls physical devices such as the cooler, heater, buzzer. Setting TRIC to output ensures the microcontrollers can drive these components instead of reading from them. LCD initializing is performed at the beginning to ensure the display is properly configured before sending any data. LCD requires a specific initialization sequence, and skipping this step would result in blank or corrupted display. The startup message is displayed to indicate the system has booted successfully. This is important in embedded system products to differentiate between a powered but faulty system and a system that is operating correctly. The while one loop is used because embedded systems are designed to run continuously, unlike normal programs. They do not terminate, instead, they continuously control hardware in real time. Inside the loop, the cooler is turned on deliberately before the heater to demonstrate cooling mode operation. The heater is explicitly turned off to avoid conflicting outputs reflecting real AC safety logic. The buzzer is activated alongside the cooler to provide an audible indicator of the system activity. This mirrors the real applications where sound feedback accompanies operational changes. So the delays are added. So as we can see, the ports are connected to the LCD. Delays are added not for the functionality but for demonstration clarity. Without delays, the on and off states would change too fast to observe on the stimulator. Finally, turning the cooler and the buzzer off and updating LCD demonstrates controlled shutdown and behavior, which is essential in embedded systems to prevent abrupt hardware. This project demonstrates how a PIC16F877A microcontroller controls an AC system by coordinating hardware outputs and user feedback using embedded C programming and real-time simulation.
To conclude this project, the AC controller logic was successfully designed, implemented, and testing. This project gave me strong hands-on experience with the PIC 16 F877A microcontroller and its peripherals. I gained a clear understanding how embedded C is used to interact with hardware, managing timings, and control real-world devices. Overall, these projects strengthened my knowledge of embedded systems, automation controls, and microcontroller based designs, making it suitable for academics use and technically demonstrations and internship evaluations.